Good afternoon, folks.
Good afternoon.
Good afternoon. How's everybody doing today? Happy Monday. Happy Monday. It's nice and sunny out. Hopefully everybody gets a chance to go outside. Thank you, Sani, for remembering to change your name. Thank you, Joanna. Let's make sure that we throw those pronouns in. Just make it the norm. Okay. Let's see here. All right, as a reminder, if you could just edit your name on Zoom to include your pronouns, that would be greatly appreciated. All right. And then we'll get started. All right, we got some good stuff to talk about tonight. We'll see where we end up at the end of our afternoon session. Let's see here. Okay. So this is our second talking about understanding the night sky. Last week, if you recall, we finished up talking about the motions of the Earth and the motions of the Sun, where we talked about Earth's, excuse me, wow, I'm so tired. We talked about the motions of the Earth around its axis, and we talked about the motions of the Earth around the Sun. Right, so we've discussed rotation and revolution. We sort of introduced the idea that Earth's rotational axis is tilted with respect to its orbital plane around the Sun. And for that reason, we experience seasons on Earth. Right? We have winter, spring, summer, and fall, not because the Earth gets closer to or farther from the Sun, but because due to Earth's tilt, part of the Sun's rays are more intense in one region of Earth and less intense in another. And that's what causes a difference in Earth's heating. So we're going to move on today. Rotation is responsible for day and night. Actually, just 2 days ago, we had the first day of spring, which is called the vernal equinox, meaning equal night. It's 12 hours of daylight and 12 hours of darkness in the same day, no matter where you are on Earth. So whether you're in the northern hemisphere or the southern hemisphere, everybody had 12 hours of daylight and 12 hours of nighttime. And for us in the northern hemisphere, that means we just passed the midway point between the shortest day of the year and the longest day of the year. Right? So now as we go forward through the end of June, our days are going to stretch longer and longer and longer until we have like 15 hours of daylight. There is a third motion of the Earth, though, that most people are not familiar with. And that is this idea of precession. That Earth's rotational axis itself wobbles around. And so how many of you have ever played with a spinning top before? Just use the hand emoji through Zoom. Okay. Ed's the only one? Did y'all not have childhoods? What's up? All right, so if you take you take a spinning top and you give it a twist and it spins on the table, the rotational axis also wobbles. All right. Hey there, Zach. All right. Let me see here, actually, being that so few people know what a spinning top is, or at least most people seem to not know what a spinning top is. Let me very quickly pull up a video for you. It's worthwhile to show.
Good afternoon. Sorry, I was having audio issues.
That's okay. You said yes to the question barrier?
Oh no. I'm just saying I didn't hear you, or that's why. So I was going through my audio settings.
No problem. I was just asking if anybody had ever played with a spinning top before. And,
Oh yes, I have.
okay. So I just want to, for everybody that is not, I'm just going to show a quick video. Okay, here we go. All right, can everybody see my screen? Really, it's saying content not supported? What the hell, that's dumb. Okay, let's try this again, hold on. Maybe it's just because it's the app. Maybe we just go straight through YouTube, we'll get something. Let's let Alex in. Spinning top. Now let's try. What the hell? It doesn't let me show shit on YouTube? Pardon my French, but this is screwed up. All right, well, that sucks. Looks like y'all are just gonna have to look up what a spinning top is on your own. All right.
You can send us the link to watch it.
So Earth's rotational axis wobbles is the main idea. All right, it looks something like this. So Earth's axis is tilted, but the direction of the tilt changes. So right now, our rotational axis points towards Polaris, right? Which is why we call Polaris the North Star. But any star can be the North Star if it lines up with Earth's north celestial pole. And the idea here is that the celestial pole swings around, right? And so at some point in time, Earth's rotational axis will point towards the star Vega, which is in a different part of the sky, right? It's a different constellation. And that will be Earth's new North Star. Are there any questions here? I feel like this is probably really confusing if you don't know what a spinning top is. And I don't know that, I have a really hard time believing that you have not seen a spinning top before. So either you're just not being chatty today, or this is not making much sense. So which is it in history class? Spinning top in history class. Okay. All right. Well, if everybody would take a moment and go to YouTube and just type in spinning top, 2 words. One of the videos that pops up first says in big yellow letters at the top, forever spin. And if you click on that video and you go past the ads and you let it start playing, you can sort of see how the handle of the toy spins around, wobbles, as the toy itself spins and rotates on its own axis. Okay, well, I'll let you all play with that. Okay, so we talk a lot about astrology, and this is sort of like a big kick in the, a big kick in the face to astrology, because the sun, the constellations of the zodiac are only so because of how Earth's tilted. But if Earth tilts and points in a different direction, then Pisces, Taurus, Sagittarius, Libra, Leo, Cancer, Capricorn, all that, they're no longer part of the zodiac. So, and that, even then changes. At the time that, people started coming up with like the themes of the zodiac, since then, Earth's axis and whatnot has shifted. So the constellations don't even line up with the original assignments of zodiac signs. Just an interesting fact. Okay. So to put together some of what we just talked about with what we talked about last Monday, the seasons are caused by Earth's tilt in its axis. Right, as a result of this tilt, when the Earth's on one side of the sun, the southern hemisphere gets more direct light. When Earth's on the other side of the sun, the northern hemisphere gets more light. And that causes a differentiated heating of the surface. So one hemisphere is usually warmer than another. Right, and that tilt over the course of a year doesn't change, right? The 23.5-degree tilt of Earth's rotational axis stays constant throughout the year. Over the course of the year, that orientation also doesn't change, right? So like, let's say that my head is the sun and this arm represents Earth's rotational axis, where this hand here, actually, let me use this pen instead. Let me pick a darker one. Here we go, so it might be easier to see. So this is Earth's North Pole, this is Earth's South Pole. All right, over the course of the year, the Earth revolves around the sun without changing the direction that its axis is pointed. Right, so it's always pointing up that way, whether it's on this side of the sun or on this side of the sun. Earth is not doing this. Right, it's not changing the direction of its axial tilt as it goes around the sun. The tilt stays in the same direction. However, over 26,000 years, right, so 26,000 times of the Earth going around the sun, the Earth wobbles once. I'll show you this from a top-down view. The Earth does this. Right, or from a side view, it spins around. Right, it completes one full wobble every 26,000 years. So right now, Earth's axial tilt is directed towards the star Polaris. 13,000 years from now, it'll be directed at the star Vega. And then after another 13,000 years, it'll be directed towards Polaris again. All right, and that change is very, very slow. It takes a very long time. Okay. Oh, that should say why, not what. Why does the moon go through phases? Pardon my my typo. I was just editing my slides and I did not catch that. Why does the moon go through phases? All right, so we're done talking about Earth motions for a moment. Before we pass this slide, does anybody know any of the names of the lunar phases?
Waning gibbous, waxing gibbous. That's just a few of them. Full moon, like half a moon.
Full moon,
Crescent.
waning gibbous, waxing gibbous. All right. What about some other ones? I think, did you say a half moon, Zach?
Yeah, I did.
Okay. It goes by a different name, but it does look half illuminated. Thank you, Jasmine. First quarter moon. What else? Any other names that we can think of?
New moon.
New moon.
Waning gibbous, waxing gibbous, full moon. Wait, I think someone already said full moon.
Yeah, we did, but that's
Okay.
other than waning and waxing gibbous. Are there any other types that involve waning and waxing?
Someone said in the chat, waning crescent.
Waning crescent.
Yeah, and waxing crescent as well. Yeah.
And then there's a third quarter moon as well. So why does the moon go through phases? What do you guys think is happening that causes us to see these different looking moons?
It's due to the position of the moon and the reflection of the sun hitting the moon.
All right.
I get confused with the lunar eclipse because it's not necessarily the Earth is in its way, or maybe it is. I'm a little off on that.
All right, we're actually going to talk about that today. But are you getting that? Did you know that from doing the lab, Ed, or is that from your prior knowledge?
In the prior knowledge.
Okay. All right. In the chat, it is not because Earth is rotating. The rotating Earth just causes the moon to appear to rise and set. But the Earth's rotation is not what causes the change in the lunar phase. So it has to do with, as Edward was just saying, where the moon, Earth, and sun are relative to each other. So if you're looking at the slide here, right, the sun is all the way on the top right corner, and it's very, very far away by comparison to the distance between the Earth and the moon. And so that light's coming in, and if you were to draw a line from the sun to the Earth, and then from the Earth to the moon, that creates an angle, right, between those 3 points. You connect 3 points with a line, or with 2 lines, you get an angle. And as the moon revolves around the Earth, so that's another celestial motion that we have yet to talk about. As the moon revolves around the Earth, the positioning changes, right? So when the moon is between the Earth and the sun, we see what's called a new moon, right? Take a look here at these 8 positions, A, B, C, D, E, F, G, and H. Notice how in all 8 of these positions, half the moon is illuminated and half of the moon is dark, right? Is not illuminated, right? So the moon is always 50% lit up by the sun. The question is, can we see the part of the moon that's being illuminated? So during a new moon, you can sort of tell here that the bright side of Earth, the illuminated part of Earth, is looking at the dark side of the moon, right? And so you would barely see it in the sky. Now, an interesting point. So the dark side of the moon is, yes, well, okay, so I think, let me address a possible misconception. There is a difference between the dark side of the moon and the far side of the moon. The far side of the moon, so imagine this, okay? Has anybody here, just again, please engage in this question, use the emoji, use one of the emojis, doesn't matter which. Has anybody here ever had an older sibling or parent swing you around, like pick you up off the floor by your arms and swing you around while you were younger. Or maybe now that you are all adults, you've picked up a younger sibling or a younger cousin or whatever and swung them around. Okay. So if doing like the person that's in the adult's role, right? So there's the adult and the child. The adult is kind of like the earth and the child is like the moon, right? Where the earth doesn't really orbit around the moon is orbiting around the earth, just like the child orbits around the adult. But when you're swinging a child around, you're always looking at their face, no matter where they are around you. Does that make sense? Right, like as you're swinging the child around, no matter where they are in the swing, you're always looking right at their face, right? It's not like you can like start to see like their side or their rear as you're spinning them around. It's kind of the same idea with the earth and the moon. We say that they are tidally locked with each other. And we'll get more into what that means later on. But because they are tidally locked, no matter where you are on Earth, if you're facing the moon, you can only ever see one side of the moon, right? There's only one face of the moon that presents itself to the Earth. So there is a far side of the moon that we on Earth will never get to see. But that's not the same as the dark side of the moon, right? Because the part of the moon that we can see, some of it can be illuminated, some of it cannot be illuminated. It just depends on where they are, where the Earth, Sun, and Moon are relative to each other. So I wanted to just address something that I heard the other day when we were talking about day and night. I was asking about what's the difference? And I believe, if I remember correctly, somebody was saying, well, during the day, the sun is out, but at night, the moon is out. And that's not always true, right? There are a lot of times, half of a month, where the moon is out during the daytime, while the sun is also out, right? And during a new moon, the sun and the moon rise together. The moon is not out at nighttime at all. It's only out during the daytime. So in the new moon position, people on Earth, as the Earth rotates, will only see the dark side of the moon while the illuminated side faces the sun. Then, I don't know if you can see these tiny little arrows in this larger bold circle, but as the moon orbits around Earth and goes from position A to position B, due to the new angle, this opening angle between the sun, Earth, and moon, right, we can now start to see the right side of the moon, right? And it's a crescent shape. Right? This is our waxing crescent phase. Waxing just means that the moon is in the process of becoming more illuminated. Right? So while the waxing crescent moon is going to get even more illuminated in the next night. Waxing gibbous, the moon's going to get even more illuminated. But when you start to get into the waning moons, waning gibbous, waning crescent, the moon's starting to become darker and darker, and it's getting closer to a new moon again. So, fast forward, so we go from new moon to a waxing crescent, or you can start to see, if you look just beyond the position of the moon in the diagram, it actually shows you what the moon looks like from Earth, right? So a new moon, you don't really see any of it, maybe a sliver. A waxing crescent, the right side is illuminated. This is like your characteristic moon shape in a cartoon. It's always a crescent moon, almost always. And then we get to our first quarter moon. And this is where a lot of people tend to get confused. Because if you're standing on Earth and you're looking at a first quarter moon, you're going to see that half of the moon is illuminated and half of the moon is not illuminated from your perspective. So why is it called a first quarter moon and not a half moon? Anybody think they have the answer to that?
I think it's because it's when it starts getting more and more illuminated, and the half moon would technically be the full moon, and then the new moon would be that. I don't know. I'm spitballing.
Well, no, Ed, that was fine. You're starting, so you're on the right track. You're conflating two separate ideas. So let me separate them for us. The first is that you're talking about the percentage of the moon that's illuminated, right? So when you're talking about a half moon, you're saying you're sort of implying half the moon's illuminated. But when we talk about these phases, first quarter moon to third quarter moon, right? The moon goes through a cycle of phases, right? This new moon to full moon, back to new moon, back to full moon, back to new moon. This cycle repeats itself, every 4 weeks or so. So when we say a first quarter moon, what we're saying is that the moon is 1/4 of the way through the cycle. Going from position A to C is 1/4. Going from C to E is another quarter. All right, so as we go from a new moon to a full moon, that's half the cycle. And then the other half is going from a full moon back to a new moon. So you can see how this is divided up into 8 slices, right? Every 2 slices makes a quarter of the lunar cycle. So A to C is the first quarter. C to E is the second quarter. E to G, that's the third quarter. So by the time the moon has gone from the new moon phase all the way around to position G, it is now a third quarter of the way done with its cycle, or 3/4 of the way done with its cycle. And then the last quarter brings it back to a new moon. All right, so
This is off topic, but does the moon have an elliptical orbit around the Earth, or
it does
okay.
have an elliptical orbit.
Does that cause? Is that the reason why there's low tide and high tide?
No. We have low tide and high tide because Earth rotates. Again, that's going to be a whole separate conversation barrier.
Oh, okay, sorry.
No. It's important enough that we actually dedicate a whole lesson to, or part of the lesson to that. We're not going to talk about it today, though, but we will. We will talk about tides, I promise. All right, so the moon rises and sets at different times depending on what phase it's in. So in blue, in this like light blue or cyan, it's saying what time the moon is the most overhead in your sky. So during a new moon, think about it, the new moon is basically in line with the sun. So during a new moon, the moon will be highest in your sky at noon, when the sun is also highest in the sky. If you zip all the way around halfway through the cycle to a full moon, look at the alignment here. You have the sun on one side of the Earth and the moon on the exact opposite side of the Earth. So if the sun is highest in the sky at noon, it will take the Earth 12 hours to rotate around for the moon to be at its highest point in your sky. So the moon would be at highest at midnight, right? Based on this idea, or based on what we're seeing here, we know that. Let's actually go with the full moon. Let's stick with the full moon for a second. The full moon's highest at midnight, which means it had to have risen before midnight, and it will set after midnight. Well, how much before? How much after? It's about, the moon's in the sky for about 12 hours at a time. So if the moon's highest in your sky at midnight, it's rising at 6 p.m. 6 hours later, it'll be midnight. And then after another 6 hours, the moon will set. So the moon rises at 6 p.m., sets at 6 a.m., and is highest in the sky at midnight. And as you go around, you can just start basically adding 3 hours to each of those times as you go through these phases. So a new moon will rise at 6 a.m., will be highest in the sky at noon, and will set at 6 p.m. A first quarter moon will rise at, let me do math correctly. A first quarter moon will rise at noon and will set at midnight. A third quarter moon will rise at midnight and set at noon. And here's a list of moon rise and moon set times. And you can notice that there's a pattern to them as we go from one phase to the next phase. These are in order, by the way. We're basically adding 3 hours to go from the time it rises to the time it's overhead. You add 6 hours. And then to go from the time it's overhead to the time it sets, you add another 6 hours. So rise and set times are 12 hours apart. If something rises at 9 p.m., it sets at 9 a.m. If it rises at 3 a.m., it sets at 3 p.m., so on and so forth. All right, are there any questions here? Is there anything that you'd like for me to clarify? Okay. Well, then let's move on. So the next question, well, it's actually 2 questions. What causes eclipse, but also what is an eclipse? Take a moment and type your answer into the chat, please. What is an eclipse?
What type of eclipse?
What do you mean, Ed? There's more than one?
There's 2, I think, which is a lunar and solar eclipse, where when for a lunar eclipse, the Earth is covering the moon, and I don't know if the moon turned red because of it or the moon just completely disappears. A solar eclipse is the moon covering the sun, and that's why everyone goes out and sees it, because it happens like so few and far between. That's all I got.
About how often do those eclipses happen? Do you know?
No, but Google does. I could Google it.
I know the answer to that question. Google does know. Yeah, Zach's getting there, right? So, like, there are 2 seasons a year, like two times in a year where you might have eclipses happen. And we'll get to that in a moment. Okay. Joanna, I like that definition a lot. It's very textbook. I like it. It uses excellent words. An obscuring of the light from one celestial body by the passage of another between it. So here's an example of an eclipse, or sort of why we have eclipses. Earth casts a shadow. So does the moon, right? So basically we have a star that we're orbiting, and that star emits light, and that light is blocked by the Earth. Now, oftentimes when we think of shadows, right, we think of 2-dimensional things, right? The shadow is 2-dimensional, right? Right? On a hot sunny day, you could stand outside, you could look down at the ground, you could see the very fine line of your shadow on the cement. But a shadow is not 2-dimensional. And I think that's the first sort of mental obstacle that you have, the mental hurdle that you have to jump over, is that shadows are three-dimensional, right? You just don't recognize the shadow until you are, until, you know, you're seeing it cast on a surface. But if I may just turn my light on. Right. My hand casts a shadow on the table here. But my shadow is in this entire region behind my hand, right? My shadow is not just the outline on the table. My shadow is this entire region where no light is passing through my hand, right? All the light from my little lamp is being blocked, right? So shadows are three-dimensional. And so in the PowerPoint slide, all right, you're sort of looking at how the sun, you know, if you look at the top part of the sun, we can draw two lines coming from it. Right? From the top of the sun, we have two lines. Let me draw this in red. Actually, I'll draw it in the black line here. So there's one line that goes from the top of the sun, where the light from that point is going towards the top of the earth. And then also from the top of the sun, we could draw a line where that light is hitting the other side of the earth. All right. So that both sides of the earth can see the top of the sun. Now we're going to do the same thing for the bottom of the sun. So the light from the bottom of the sun reaches the bottom of the earth. The light from the bottom of the sun reaches the top of the earth. What we have here is Earth's shadow, and the shape of the shadow is a three-dimensional cone. Right? It's sort of hard, it might be a little bit hard to see. Okay, so I'm going to put a little line here. Right, so it's a 3D cone where light is being blocked. Now, there are two regions to Earth's shadow. There's what's called the umbra and the penumbra. The umbra is the darkest part of the shadow. It's where, you know, if I were standing, if I were in my little spacecraft and I were hanging out in the umbra, I wouldn't be able to see any part of the sun at all, right? Because both from this position, the top and bottom of the sun are being blocked from my view by the earth, right? So from this little person's perspective, the earth is eclipsing the sun. But then there's this person up here with the long arms, okay? Now, for this person, it's not totally eclipsed. So I'm going to need a different colored pen here. Let's get out the red pen. So from this person's perspective, they can see from their line of sight the top of the sun. And then they can look along the edge of the earth here. Right, and see part of the sun, but the bottom part here is all obscured, right? This part of the earth, excuse me, this part of the sun is out of view for this person with the long arms because the earth's blocking it. So if you're standing in the umbra, the sun would be totally eclipsed. But if you're in the penumbra, the sun would only appear partially eclipsed. Does that kind of make sense? Are there any questions on that? And so there's a little bit of a
I'm sorry, can you repeat what you said last?
Sure. So a person that's standing in the umbra, so this person that I'm circling in red, that person would not be able to see any of the sun at all. From their perspective, the sun is totally eclipsed by the earth. But then there's this person up top who looks like they have the lasers coming out of their eyes. That's just their field of view, right? That's how much of the sun they can see, because this bottom part of the sun, let me change colors one more time. Let me go to, I don't know, blue. From the bottom part of the sun to that person, right, this light is falling on the earth. So the person that's back here can't see this part of the sun, but they can see the top part of the sun. Right, and so for the person that's on the top, who I'm drawing a little arrow to, they can see a partial sun. They're getting a partial eclipse, but not a total eclipse. Did I clarify?
So in a way, does it kind of look like a half sun?
Yeah, it might. Well, it could be half. It could be more than half. It could be less than half. And we'll see actually what that looks like in a second, because I'm gonna pull up a video or two for us to watch. One for solar eclipses and one for lunar eclipses. So let me just erase these lines. Okay. So the eclipses that we get are caused by shadows cast by the Earth and the Moon. And an eclipse can happen when either passes through the shadow of the other. And I think Edward was saying, you know, when the moon passes through the Earth's shadow, we see a lunar eclipse, right? The moon is being eclipsed by the Earth, right? So sunlight doesn't fall on the moon gets dark. But when the moon passes between the Earth and the sun, the moon is blocking some of the sunlight from landing on Earth. And so that's when we get a solar eclipse, right? Where from Earth's perspective, the sun is being blocked out. All right, so here are just your definitions for umbra and penumbra. All right, the two regions of the shadow here. All right, so you can sort of see, like, if you have a wide enough light source, this actually might even be easy if you're in a room that has two light sources. If you look at like the leg of a chair when light is cast on it, there's usually, like, you can typically see like a very fine shadow, and then sort of how it gets like fuzzy on the sides. I wonder if I can like sort of replicate that with anything that I have here around me. Let me check. Okay, let me see if I can make this work. Let me try this. I think I can make it work. Okay, so you see how I have my lamp here. And can you guys sort of see how in this spot right here, like the shadow sort of comes to a point? Is that clear for you?
Yes.
Okay, so the shadow comes to a point here. This region is the umbra, but there's a part over here where you can see maybe a little bit that it is darkened. It's not as dark as the umbra, but it's darker than if I didn't have my pen there at all. This is the penumbra. right? The penumbra is this slightly darkened region here. So if you were a tiny little person standing on the surface of this table, looking up, you would be able to see part of the light, but not all of it. If you were standing in this spot in the umbra and you were trying to look through the pen at the light bulb that's up there, you wouldn't be able to see it at all because it's totally being eclipsed by the pen. All right, so let's move on. Okay, so there are three kinds of eclipses that we talk about when it comes to lunar eclipses. There are total lunar eclipses, there are partial lunar eclipses, and there are penumbral lunar eclipses. And you can see here in the blue font exactly what that means. Right, so a total lunar eclipse means that the moon is passing completely through Earth's umbra. Right, there is no direct sunlight falling on the moon's surface. Then we have a partial lunar eclipse in which part of the moon passes through the umbra, part of it passes through the penumbra. And you can see here very clearly that this darkened part, this is Earth's curvature. Right? One of the several ways that we know Earth is round, is spherical rather. Being that, sorry, I just totally lost my train of thought there, got distracted. But you can see how the part of the moon that's in Earth's umbral shadow is totally darkened, and the part that's passing through the penumbral shadow is partially darkened. Here you have a penumbral lunar eclipse where the moon totally passes through the penumbra. You might not even recognize it if you were to see it because it's, its illumination is such changes very subtly. But what we have here, when we get this kind of alignment of three celestial bodies, like in this case, we're looking at the sun, the earth, and then the moon, we call this a syzygy. It's a great word, S-Y-Z-Y-G-Y, a syzygy. So let me pull up this video here. Oh, come on, what the hell? It's fine. Give me a moment. We're going to close that for a second. I'm just going to share another screen. Maybe YouTube will stop being a piece of crap if I do it through my computer. No, my iPad. Okay. There we go. Okay, that's the one. Gosh, it's not.
A lunar eclipse happens when the Earth blocks some or all of the sun's direct light from reaching the moon. This cosmic event only takes place during a full moon, which happens once every 29.5 days, or the length of one full orbit of the moon around the Earth. So why don't we have an eclipse every month? The moon's orbit is tilted a few degrees in relation to the Earth, so the Earth, Moon, and Sun don't always align. When the Earth does eclipse the Sun, it casts two types of shadows on the Moon. A larger shadow, known as the penumbra, and a smaller, darker shadow, known as the umbra. There are three types of lunar eclipses. The first is a total lunar eclipse, when the Sun, Moon, and Earth are in perfect alignment and the Moon falls within the Earth's umbral shadow. Total lunar eclipses are the most striking of the three types because they turn the Moon a sunset red. While shorter blue wavelengths of light are scattered outward by the Earth's atmosphere, longer red wavelengths are refracted or bent inward toward the moon, making it appear red. The brightness of the moon's red glow depends upon how much dust and clouds are in the Earth's atmosphere. Following volcanic activity, ash can block out enough light to render the moon a darker red or even near black. A partial lunar eclipse, the second type, occurs when the Earth, Moon, and Sun don't perfectly align, so only part of the moon passes into Earth's umbra. Earth's shadow appears very dark on the side of the moon facing Earth. Last, a penumbral lunar eclipse occurs when the moon passes through Earth's penumbral shadow. The event is so subtle that most people don't even notice. The moon will appear just slightly darker than normal. Lunar eclipses occur up to 3 times a year and can be observed from the entire nighttime half of the Earth. Unlike during a solar eclipse, it's safe to look at the moon with the naked eye during a lunar eclipse. It is only because of the distances of the sun and moon from the Earth that we are able to witness total lunar eclipses. As the moon inches away from the Earth each year, one day, billions of years from now, the moon will be too far away to fall completely within Earth's umbral shadow. Until then, we can occasionally enjoy seeing our own planet's shadow cast upon the largest object in the night sky.
Okay. All right, any questions following that video? Anything there that you heard that you wanted to ask a question about?
Actually, there's something that did interest me, which is they're talking about the volcanic ash creating residue and stuff. I didn't know it goes up to like the atmosphere and space and stuff. Is that what happens? Is it like a satellite kind of thing?
So what happens is when light passes through Earth's atmosphere, the light bends. Kind of like how you ever get a rainbowing effect as light passes through glass?
Okay.
Right, so it's like sunlight is comprised of all of the different colors of the visible spectrum. And so when that light hits a piece of glass, it disperses the light into those constituent colors. Now, when sunlight hits the Earth's atmosphere along the edges of Earth, sunlight is refracted around the Earth on all sides. The blue lights get scattered outward and the red lights refract inward. But that's why the sun turns red. So when there's a lot of volcanic ash in the atmosphere, not that the volcanic ash is being ejected into space, but that it's in the atmosphere, that ash blocks the light from going through. And so instead of the sun turning a red color, it just gets totally dark because the ash is preventing the red light from going all the way around.
Okay, that's what I wanted to ask. Thank you.
You're welcome. All right. Any other questions? All right, so got a couple minutes left. Let me pull up the next bit here. All right, so that brings us to solar eclipses. There are 3 kinds that we talk about. Right, there are 3 kinds of solar eclipses. We have total solar eclipses, partial solar eclipses, and annular solar eclipses. We may also talk about a 4th kind, which is called a hybrid. Did I just say lunar? I meant solar if I did. But a hybrid solar eclipse. And so if you take a look here, I know that it's a little bit small. Let me zoom in on that. Can you guys still see it? Yes, no, maybe so. So in this kind of alignment, right, we have the sun, then the moon, and then the earth. That's different than a lunar eclipse where we had sun, earth, moon. Right now we have sun, moon, earth. And the moon's shadow is, the moon's umbral shadow strikes a point on earth. That's called the path of totality, right? Where this umbral shadow sweeps out a path across Earth's surface as Earth rotates underneath it. We have the path of totality, and anybody standing in that path would see this, a total solar eclipse. Anybody standing in the umbral shadow, the penumbral shadow, so the lighter gray region, would see that the sky gets darker, but it doesn't get totally dark. And they would still be able to, you could still see the sun. All right. In a partial solar eclipse, depending on whether or not you have a special device, you could actually see how much of the moon is eclipsed, how much of the sun is eclipsed at any given point in the eclipsing process. And then last but not least, we have what's called an annular solar eclipse. And what happens here, so there are some times, because the moon's orbit is elliptical, there are times where the moon is closer to the earth and times where it's farther from the earth. And as a result, the moon appears slightly larger or slightly smaller in our sky. The Earth's orbit around the sun is also elliptical, right? It's not a perfect circle. So there are times where we are closer to the sun and times where we are farther from the sun, in which case the sun could either appear slightly larger in our sky or slightly smaller in our sky. Now, it just so happens that Earth is in exactly like the perfect region where the moon and the sun are just about the same size in the sky. As a result, it is possible to pass through the umbral shadow. Hold on one second. All right, I'm sorry. It's possible to pass through the umbral shadow as we do here, but it's also possible to pass through the part of the umbral shadow after these two rays sort of converge at this point. So you can kind of see where my mouse is on the screen here, how it's touching the tip of this cone shape right over there. But beyond that cone, the lines crisscross and there's another umbral shadow. In this part of the shadow, let me just show you the video. Because my brain's melting and me trying to explain this while my brain's melting is not a good idea. I need to finish my lunch. That's what needs to happen. Okay, so let's open up National Geographic. We're going to look at solar eclipses now. Here we go.
The biggest challenge was the timeline.
How are we going to do this?
A solar eclipse happens when a new moon moves between the Earth and the Sun, blocking some or all of the Sun's rays from reaching the Earth. By cosmic chance, even though the Sun is 400 times wider than the Moon, it's also 400 times farther away. Therefore, the two objects appear the same size in our sky. Astronomers are able to predict eclipses because the Earth and Moon have very predictable orbits. Why then isn't there an eclipse every month? The Moon's orbit is usually tilted a few degrees north or south in relation to the Earth. When the Moon does eclipse the Sun, it casts two types of shadows on Earth: a smaller, darker shadow known as the umbra, and a larger shadow known as the penumbra. There are 4 types of solar eclipses. The first and most spectacular is a total eclipse, when the moon completely covers the sun's surface. A total eclipse can only be seen if you're standing within the umbral shadow. That's why the imaginary line created by this shadow as it races across Earth is known as the path of totality. People within the penumbral shadow see only a partial eclipse, the second type. From this view, outside the path of totality, the moon passes in front of the sun off-center, never fully covering its surface. Third, an annular eclipse occurs when the moon passes directly in front of the sun. However, unlike a total eclipse, the moon appears too small to fully cover the sun. The moon's orbit is elliptical, so sometimes it's closer to Earth and sometimes it's farther away. Last, a hybrid eclipse is when the moon's position between the Earth and sun is so finely balanced that the curvature of the Earth plays a role. The moon will be farther away from some parts of Earth along the eclipse's path, resulting in an annular eclipse. In other parts, the moon will be just close enough to fully cover the sun, resulting in a total eclipse. While a total solar eclipse happens somewhere on Earth every year or two, any given point on Earth experiences the event only about once every 400 years. We interrupt this video for an important safety announcement. Looking directly at the sun, even during an eclipse, can cause permanent eye damage. Fortunately, there are ways to enjoy an eclipse safely. The easiest is to use certified eclipse-watching glasses, which are shaded thousands of times darker than typical sunglasses. You can also look at the eclipse indirectly by making a pinhole viewer. Simply poke a small hole in a piece of cardboard. Hold the cardboard up to the sun, allowing the sun's image to be projected onto a flat surface. Be sure to look only at the surface and not through the cardboard. Just before the moon completely covers the sun, low-lying valleys on the moon's edge will be the only spots that sunlight continues to pass through. These remaining brilliant shafts of light, known as Bailey's beads, will disappear one after another. And finally, a single bead of light remains, known as the diamond ring, signaling that you're just seconds away from experiencing totality. Once the last bead disappears and the moon completely covers the sun's surface, the view through your eclipse glasses will be pitch black. Totality achieved. At this point, none of the sun's rays are reaching your eyes, and it's the only time that it's safe to take off your glasses. Remember to put your eclipse glasses back on before any of the sun's rays start to peek through again. Any sunlight reaching your eyes, even for a few seconds, can cause serious damage. While an eclipse can last a few hours, totality typically occurs for less than 3 minutes. Animals and plants have also been known to alter their behavior during a total eclipse. Songbirds may stop singing, crickets may start chirping, and flowers may even start to close up. We won't always be able to see total solar eclipses. The moon moves about 1.5 inches away from Earth each year. It's estimated that in about 1 billion years, the moon will be too far away from Earth to completely cover the sun.
Okay. I always find that so fascinating. I love those videos. Very quickly, I'll just put up one more slide for you to finish copying, and then the rest of this lesson will get picked up by the evening section. And with that, once you're done getting this information, you are good to go. So if anybody has any questions, I'm happy to answer them. Otherwise, enjoy the rest of your week. Next week we have off. It is spring break, so there are no assignments due, at least not that I can recall. I would double check that. Let me make sure before I say something incorrect. So I'm going to open my notes real fast. Hold on, please. I'm sorry, there is something due on this Sunday, Lab 2. So Lab 1 and the first homework set were due yesterday. Lab 2 is due next Sunday, which means there's also probably a discussion due this on Sunday the 28th. That being said, the week of spring break, there's nothing due. So there will not be anything due on April 4th. All right, so there are 2 assignments due this week, the solar simulator and discussion 3. There will be nothing due on April 4th. Sorry that I said that incorrectly at first. All right. Yes, Chris. And then on the 5th, we'll be back. We'll be back in class on the 5th. And so you only have to do Lab 2. So right now you should have completed discussion weeks 1 and 2. You should have completed Lab 1. You should have completed homework 1. This coming Sunday, you have Lab 2 and discussion week 3. Lab 1 is on Blackboard under the homework and lab tab. Right, all of our homeworks and labs are in that tab.
I think I missed the homework. Can I still do it or not?
Yes, you can.
Okay, thank you.
Okay. Yes, it is first problem set. It says it on the calendar in the syllabus, right? Go by the syllabus, Alexa. For some reason, Blackboard's not letting me post. It's not showing the due dates on the calendar, on the class calendar. It is showing when I open the assignment up to edit it that there's a due date. So I don't know why it's not coming up through Blackboard, but that's why it's important that you have the calendar, right? The syllabus, because the syllabus has all of the due dates for all of the lab and homework assignments. All right. And Chris, it is called first problem set. It's called first problem set. All right.
I have a question.
Sure.
Is the lab and the homework two separate thing? Because I don't see the homework.
They're in the same tab.
Yeah, but I see only first problem set. I did that, but I don't see the homework.
That is the homework. First problem set is the homework.
Oh, okay.
So let me just quickly pull it up here on Blackboard just in case anybody watching this and maybe has a similar question. So if I share my screen, okay, under our Blackboard page, we have homework and labs on the left side. The first problem set is homework 1. And then down at the bottom, these ones that don't say problem set are all labs. Right, so there are 5 labs here: phases of the moon, solar simulator, gravity and orbits, force of gravity, black body spectrum. If you look at the syllabus, right, it gives the due dates for all of these. Right, and it says exactly what's due and when. Okay.
Oh, Professor, I didn't know that there were like different due dates for each of them. I was just following the order of the homework. So I probably missed the first lab. That's the.
Okay.
So I was wondering if I could redo it or something.
As soon as possible.
I also didn't do it, but I am on it right now, and it says that this assignment was due. It's only giving me the option to practice it now, not to be able to do it.
I will fix that.
Okay, thank you so much. Sorry for that.
Thank you. Yeah.
No problem.
Professor, one more thing. The recording, I couldn't find the second one.
What do you mean?
The second recording for the second class that you have in the evening, I couldn't find it on the class recording. So I only see lecture 2.1. I also see lecture 2.2.
Wow, that is absolutely my fault. I'm very sorry about that. I did not ever get to post it. I am very sorry. I will
And that's
fix
all
it.
right. All right, so on the syllabus, we just have